And here we are, we're in lesson three for week 2. Now, I did want to make mention of what's on D2L. If you go to D2L, you'll see that I've got a lot of things there in the news section. There's a lot of new stuff that's added for week 2, but also for week 1. And so I think you should probably go back there and look at that. So this is all week 2. There's a lot of stuff. This is extra added to the lecture. So I'm sorry about that, but this was the stuff that was given to me, and I want to make sure that you have it. Then for week 1, I put a lot of review notes in there, including a couple of videos for you to watch. Maybe you'll find that interesting. So I'll tell you why I'm doing this, students. I'll tell you why. I want to make sure that you have every opportunity to be ready for the quiz and the test. So the quiz is not this week. It's going to be next week. I guess it'll be during the tutorial lesson, but it'll be on chapters 1 and 2. Or sorry, it'll be on the weeks 1 and 2. And so weeks 1 and 2 actually has 4 chapters in it. We did 2 chapters last week, 2 chapters this week. So all of that will be on the quiz. And so I'm just making sure, look, you got some videos to watch. I know it's a lot of content overload, but I just want to make sure that you're ready. You're sort of saturated with all the stuff that we've got so that you're ready for that exam. So that's what I'm hoping for. And yeah, so it says we're screen sharing, but all of that's on there. Please do go and have a look at all the stuff that's on D2L. As I said, if you get, just read the notes that are there. When you get tired of that, watch some videos. There's a lot of videos to watch there. I mean, you could probably set aside a few hours to watch those videos. I mean, most of them are only a few minutes long, but there's a lot of them. Okay, you don't have to. This is just my suggestion to you so that you're 100% ready to do the quiz, right? That's where we want to be. Elements of computer architecture. So in this lesson, the first lesson, lesson 3, we're going to look at the motherboard. We talked about last time Van Neumann's architecture. We're going to talk about a Harvard computer architecture as opposed to Van Neumann's. We're going to talk about, I suppose, different other components in the computer itself. Then after that, we'll talk about computer languages. We've already spent a bit of time about that, and we'll talk about algorithms. So we got a bit to talk about today. Sorry, when I say we, mostly I'm going to be talking. Sorry about that, but kind of the way it works out. And you guys can't see anything because I don't have anything on the screen. So that's not great. So try and turn that on. I'm sorry about that. Is it on now? Yeah, there we go. So we're going to talk about computer architecture. Now, what I was trying to show you before was that on D2L, we've got a lot of stuff there that I'm scrolling through on the right. That's all under the heading of news. And so basically everything that's under there now, you should at least read once before the quiz, I would say. And you can see the links for the various videos that I was referring to. Okay, so elements of computer architecture. Artificial intelligence computers become smarter than humans. We sort of talked about that a little bit last time, but just briefly. Hasn't really happened according to the Turing test, right? Got kind of close. Would they be smart? When computers can sort of actually achieve sort of artificial intelligence and general purpose, do all the things, not just in a specific context, not just doing one special task, but doing general tasks like humans, I think we're still a little ways off on that. And we mentioned that last time when we referred to like the Google cars that really can't drive like a human can drive, things like that. We're still a little ways off that. Can computers compute anything? Now, I mentioned Alan Turing. Alan Turing Alan Turing tried to approach the test of, maybe I'm a bit early on this. Maybe that's the next lesson, sorry. Yeah, Alan Turing did try to approach the test of a, could a computer meet the a test of being able to find a place to stop? That's in next lesson. Sorry, I didn't mean to jump ahead. Computers aren't smarter than people, but they can go very, very fast. And they'll only do whatever you tell them to do, right? And so we had this old saying, garbage in, garbage out. If you write garbage programs, you get garbage output. You put in garbage input, you get garbage output. But yeah, they are definitely improving on what they were capable of previously. That's the superpowers it refers to. In this example here in this cartoon, sometimes cartoons actually have a lot of wisdom in them, I suppose. Now, you have a look at this and see if you can get the wisdom. This is an age-old problem that computer people have, which is, sorry, just having, so make sure I'm in the right one. Yeah, lecture 3. Age-old problem that computer people have, which is when we go to build a new system, we're building a system for somebody. The problem is getting the specifications. What we mean is getting the person to tell us what it is they want us to do. And nowadays with rapid development, we do have very rapid development tools. You'll see that when you finish your degree here, you'll have to do a capstone project of some kind, and you'll be able to, within a few weeks, develop quite a comprehensive system. You'll find that you can use libraries with JavaScript, with HTML, with Python, and you can build some quite complex, very powerful systems in a very short time. And so because we can do that, what we tend to find is we think we get what the customer wants, and then we sort of go to build something, and then they look at it and they say, oh, you could do that. Well, now I want to change it. I want to make it like this and like that. You get to a situation where it's almost impossible to finish because the user keeps on wanting new things. That's an age-old problem. This particular cartoon series is called the Dilbert. Dilbert was a IT sort of person in the 1980s in the United States, I guess, and he was always making fun of what happens in offices with IT people. And so when you read this, it's kind of a satire, being that he's making fun of the people. And every day you'd get this in the newspaper in the 1980s. It's still available. If you're interested in that kind of, people making fun of IT people in cartoons, just search for Dilbert. There's probably, I don't know, thousands and thousands of these because he used to like do one every day. All right, so we have these two concepts of software and hardware. When we refer to hardware, we're talking about equipment. We're talking about stuff that you can touch, iron, metal, electrical things. That's our hardware. That's the computer that we see. The software is going to be the instructions that make that thing work. And so we do refer to things as algorithms that are part of the software. The software is developed from an algorithm. Yeah, so I'm just trying to think. Yeah, so I think we talked about the super cool, other problems, very difficult. Yeah, the halting problem was the problem of, so these are the notes that go with these slides. The halting problem was the problem that I was mentioning about Turing. The halting problem is, how do we know when a computer that we set off a computer program that could, it seems, go forever, or when will it stop? How can we have one that will stop? Turing came up with an answer to this question, and Turing's answer was that it's not possible to know the end of a halting problem, and he did it by theoretical approach. Turing was really a mathematician, and so he imagined that you had two programs. One program which would affect another program. When program A was running, program B would be stopped. When program A was stopped, then program B would be running. And so what Turing said is, well, what if I had program B call itself? Well, then it would always be running and it would always be not running. And so it would never halt. Anyways, there's a video on that you can watch that will explain it in a little bit more detail if you're interested. Yeah, that was the halting problem, which was put up by a mathematician in 1928. And I guess it was 36 or something like that. Turing solved the problem theoretically by that example that I gave you. I've got a chat. Got it. Okay, so there we go. So if I missed anything on there, yeah, those are, as I said, those notes go with it. So we've got some other things here that go with that. I think I should mention these little notes that go with that slide before I move on. These notes on the right. So the thing about the can computers go forever? What kind of calculations can we do? If I don't know what you know about prime numbers. Prime number is a number which is only divisible by itself in 1. And so you can do some calculations which will get prime numbers. You can multiply prime numbers by each other and then test to see if the result is a prime number. And that's important if you're into computer security, because in computer security, one of the things that we like to do is we like to send encrypted messages. So for example, whenever you use the internet to buy things, you must do that by encrypted messages. Otherwise, people that want to steal, and there's no shortage of people that want to steal, believe me, they would get your bank details and empty out your bank account or max out your credit cards. That would happen in a flash if you didn't encrypt all of your transactions. And so every time you're dealing with the bank, that's got to be a secure transaction over whatever network that's going over. Now we have some confidence in that because we have encrypted protocols that work for us. So when we're working on a banking protocol or something like that, we'll notice up in the URL, it'll say HTTPS, which means we're using a secure protocol. Now we can use encryption to send things from place to place, and that encryption will involve a key. That is, we have a special number, that's the key, and that special number is applied to create the jumble of information from our message. So we take a message, which we call plain text, and then we run it mathematically. We divide it by this special number, etc. And we get this jumble, which is just sort of random. It seems like it's random. It's not actually random. It's just that we've taken our message and we've processed it with this special number. And then nobody can read it. Well, they can see it. You know, they can sit there on the line and they can see your message, but it doesn't make any sense to anybody. The only person it'll make sense to is a person who's got the key. And so the key will be some multiple of 2 prime numbers, all right, which you have used to create a key. And that could be broken if you had the mathematical and computer ability to sort of regenerate those numbers. So, but the thing is, if you get a large enough sort of prime number, you have something which is very, very hard to compute. I mean, it's become so hard to compute that it would cost more to compute it than it would be worth in using the crack code. So that's the idea of that. That's what it means here with this RSA factoring challenge is computing these numbers by multiplying and dividing them. It talks about 2 prime factors. I hope I've sort of given you a bit of information about that. You don't need to sort of you don't need to know too much about that, other than, as I mentioned, it's a mathematical process. There's a special key. All right, it's unique, and if you had the right mathematical tools, maybe you could crack it, right? But the idea is we do keep that secret. Now, if you had quantum computers, the idea of quantum computers, it's possible that in a brute force, when we say brute force, what we mean is just using our computer to do millions or billions of calculations based on what we're trying to find, and sort of finding a number by just multiple calculations. So in a way, it's kind of possible to do that with anything, but it might take hundreds of years, you know what I mean, with the computer power that we've got. Or if you can get more powerful computers, you can do that brute force finding of the number that you're looking for quicker. And so the idea here is that maybe when we have quantum computers, that will be easier for the bad people to do. But on the other hand, the quantum computers would then be used to calculate new keys, all right, which were harder to crack. And I think you'll see that. Now, when you start doing cryptography, you'll learn about that. Well, people will talk about the key. Is it 128-bit, or is it a 256-bit key? And I guess you could guess that a 256-bit key would be much harder to sort of crack than a 128-bit one, because a lot more mathematics involved. All right, so difference between hardware and software. I hope you get the idea between difference in hardware and software. Software are going to be instructions. Hardware is going to be the machine that it runs on. So here's some examples of some hardware that you can see there on the left, I hope. I mean, most important, sometimes we use the word loosely brain. CPU is where the processing is done. P stands for processing in CPU. C for central, U for unit. Central processing unit. Central processing unit are so powerful nowadays that they produce so much heat that they have to have their own sort of heat removal, heat sink on them. And so we have a fan that is going to be removing heat directly from the CPU. And then you're going to have other fans in the case of your computer at the back there. You'll have some fans. You have one to remove heat from the power source, and you might have one just to remove heat from the box generally. Notice also we got another little fan here removing heat from your VGA card. And that's because your VGA card actually has a processor on it. Your modern VGA cards, VGA card is for your video graphics. Modern VGA cards are so powerful, they're much more powerful than some of the earlier computers were. And that's because people use them to play games and stuff like that, you know, processing games, millions of pixels on your screen, changing, you know, in millisecond time. And people who are playing games, well, my daughter's a gamer, I'm not, but I noticed that the speed is highly desirable, right? Otherwise, you're lagging and you lose the game. And so, yeah, so that's somewhere where we've gone with computing. We have some other things like, I hope you noticed there that we've got some slots in this thing here, which we call a motherboard. The motherboard is that rectangular thing there. It's got some slots along the side here. It's got some slots here. These slots here would be very close to the CPU and therefore the random access memory. The random access memory is not the only memory. All right, there's lots of other memory in the computer. We have memory that's built right into the CPU. We have these things called registers, and we have these things called caches. We have the random access memory, and then we have some secondary storage memory, which is shown by this thing here called a hard drive, hard disk. Hard disk is becoming legacy technology. When I say legacy technology, I mean technology which has been superseded, which has been obsoleted. And not now, but is becoming obsoleted. I think it's still cheaper to buy hard disk and put it into your computer than it is to buy SSD, which is the replacement for a hard disk. SSD is solid state drive. Solid state drive has no moving parts. You can get solid state drive on your laptop computer, 512 gig, 1 terabyte. Not that expensive. Just a few years ago, it was prohibitively expensive, but now you can get it. And so people are having laptops with no moving parts in them, right? Because maybe the hard disk has been replaced just by a SSD. Or you may have a combination of an SSD and a hard drive, because the hard drive is cheaper. Hard drive does have another little benefit over SSD in that SSD has been proven to degrade over time. And that is, you can lose bits of information at particular memory positions, more so than a hard drive. Card readers, we got lots of things there, monitors, lots of input things. I think that's enough for me to talk about on that. So yeah, there's some notes on that, and I've tried to cover that, but again, so there's some notes for you to refer to that will help you, and they're on the side there. If you look under your news, you'll see all of those notes are there. That will help you as you prepare for your quiz next week. Binary will be the binary to digital will be the topic of our tutorial this week. So next lesson that we have, I'll be working with you on exercises, converting binary to digital, converting binary to hexadecimal. I should have said decimal rather than digital. Binary to decimal, binary to hexadecimal. We'll have some exercises on that because that will show up in a quiz. Okay, so you'll be able to do that. But binary is just zeros and ones. From zeros and ones, we can build other numbers. So if you only have 0 and 1, you've only got 2 possibilities. It's either a 0 or a 1. But if you put a 0 and a 1 beside each other, then you've got 4 possibilities. So which one am I missing? 0, 1. I should have done 1, 0. Then I did do 1, 0. Then I should do 1, 1. Oh, 0, 0. So 4 possibilities of combining zeros and ones. And actually, when we do that, we say this is the number 1, this is the number 2, this is the number 3. Sorry, that's wrong. This is the number 0, this is the number 1, this is the number 2, and this is the number 3. And then if you went out to the next one, this would be the number 4. And then with three binary numbers beside each other, you've got 8 possibilities. So you got the number 4. Well, you could also have the number 0. Well, but you got the number 4, you got the number 5, the number 6, the number 7, and the number 8. Oh, the number 8 comes out here. All right, so and all of these numbers, right? If you put zeros in front of those, that would be your 3 numbers together. So yeah, binary is kind of cool. I got 4 chats, so it's not effective. SSD is effective. Is effective? Yes. I'm just saying that people have now the data that you're losing on your SSD is very small amount. All right. I'm just saying that you might want to do some backup on it. I think the internet connection also must be good to do. Yes, if you want to do brute force sort of attacks, you'd want to have a good connection and good computers to do it. Most people would do the attack on a computer isolated. Right, SSD is kind of cool. I think we're all going to be using SSD. All right, so what do we got there? RAM, random access memory. Yeah, all of those things. That's just notes on the stuff. I think I've mentioned that. I'm not going to go over that too much more. There's our binary and some notes on that. Now, the number of bits that you have could relate to the power of 2 of how many states you've got. So as I mentioned here, if you've only got a 0 or a 1, you can have 2 possibilities. If you've got 0, 0, 0, 1, 1, 0, 1, 1, you see there you got 4 possibilities. This is 2 to the 2, right? This is 2 to the what would that be? 2 to the 1. 2 to the 1 is equal to 1, right? Sorry, is equal to 2. The 2 to the 2 is equal to 4, and then if you got 3, what you've got is 2 to the 3 possibilities, which is equal to 8. And then if you put 4 together, you get 2 to the 4, which would be equal to 16. If you add 5, it would be. You get the idea? All right. So, for example, when we give a number for an address on an internet network, we use an IP address. IP address is made up of 4 lots of 8 octets, we call it. So a number like this, 1, 2, 3, 4. So 8 bits. 8 bits are part of an IP address. 8 bits times 4. But the 8 bits, that gives you a possibility of 256 different addresses from 0 to 256. And you could know that by knowing that would be 2 to the 8. And 2 to the 8 is 256. I hope you get that idea. All right, so the thing is, fetch decode, are we in the, yeah, okay, so, right. So how does a computer run a program? So as it says there, the program is stored in the random access memory. I hope you remember seeing in the screen a minute ago, a random access memory is on a bus that connects to the CPU. So random access memory is going to be loaded up with the instructions of the program. And then that's going to be loaded into the CPU. That's called a fetch. The fetch is going to get one instruction from the memory into the CPU. And then it's going to decode it. Okay. And after it decodes it, then it's going to do the execution. Now, what have I got here that I'm missing that's hiding behind this? Nothing. I do have something. Yes, Papa, no, Papa, no, Papa. I'm not sure what they mean by that. It sounds funny, though. All right. So time now to consider the von Neumann architecture versus the Harvard architecture. I've got some notes there beside that compare the two. I hope that you notice that the Harvard architecture is a little bit more complex than the Van Neumann architecture. And mainly that's if you look at the buses. So you see these buses here, the data bus, we've only got one data bus, and it's kind of shared between two sort of activities there, right? So it's going to get the code memory into the CPU, and it's going to take data memory either way. We've got an address bus that kind of works in the same way. And now with the Harvard architecture, we seem to have divided that out. We've separated out buses between the code memory and the data memory. So we have a different bus going to the code memory and going to the data memory, as opposed to in the Van Neumann, where the same bus had to go to both. And so with that slightly more complicated architecture, we have something that works a little bit faster. Okay, it works a little bit faster, and we use it for different purposes. So for the Van Neumann architecture, that's typically used for your personal computer. A personal computer is still using Van Neumann architecture, though the actual model was developed in the 1940s. So I hope you remember that. But the Harvard architecture is used for more single purpose sort of processors. So for example, in your mobile phone and in special environments. All right, so here we have a model showing, and the arrows basically show how this, we call it a cycle, but how this cycle is processed. So what's going to happen here is from memory, let's start at this corner. From the main memory, something is going to the control unit. Well, what's that going to be? That's going to be an instruction. That's a fetch. So the first thing we do is we fetch an instruction. That is controlled by the control unit. All right, so we fetch an instruction, and that brings us an instruction into the CPU from the main memory. Once that instruction is there, oh, by the way, this is all controlled by a clock. So the clock, a clock sort of says now, and then we read something from the memory. Then it says now again, and then we decode that information. Then it says now again, and then we execute that. And then it says now again, we go back and do it again. So every time the clock ticks, we move to the next part of the cycle until we get through the cycle. So in between the control unit and the ALU and the control unit are parts of the CPU. They are parts of the CPU. They're inside the memory. They're inside the CPU. Now I mentioned memory there because of this thing called registries. Registries is just another kind of memory. It doesn't take up too much space, but the key thing about the registries is it is so close to the CPU. It's actually in the CPU, and so it's going to be much faster writing things to it and taking things out of it. That's where things are going to be temporarily stored as we're doing the processing. When that processing is finished, we're going to put our result back out to the main memory. So the main memory is going to store our instructions. It's going to store our data that we retrieve, and it's going to store our output. It's going to go to the main memory, and wherever it goes after that. So there's a description of that there, so you have notes on that there. Okay, so the next diagram is kind of I think that's supposed to be kind of like funny or something, I guess. Maybe it's funny. And by the way, these links there, those are videos that you can watch. So there's like a 5-minute video on just what I talked about, the Van Neumann cycle. So there's lots of videos on YouTube on that, and I've given you some links on that, so you can entertain yourself and maybe learn some more stuff on that. So there's a lot of notes there about Van Neumann versus Harvard. As it says there, Van Neumann requires less hardware, less space. It's kind of ironic, right? That I sort of found that sort of hard to understand why the Van Neumann requires less hardware, but it's used in the bigger machine. It's used in the laptop, and whereas we're using our Harvard in these special devices. Okay, so there's the cycle, fetch, decode, execute, and the Power Rangers. I mean, that's kind of a weird sort of reference, but I think the idea there is the Power Rangers is all these different people, but they work together. All right. And so I think that's what you want to be thinking about here is in the CPU, we've got multiple components. It's not just one solid thing, right? There's multiple components, but they work together. So from our point of view, looking from the outside into a computer, we're just seeing the computer doing something, right? Okay, the CPU does something. So you can think of that as a single cycle processor, but it's got these things going on, right? It's doing a fetch, doing a decode, it's doing execute. Write back is putting it back into the memory where it came from. So in the memory, we have our instructions and our data. That data is fetched, then it's decoded, then it's executed, then it's what's written back is the answer. And there's an example of an analogy of that. If you were cooking and you wanted to go and cook something new that you've never cooked before, and you went and you searched on the internet, you did a Google search, and on the internet, you found this nice recipe. All right, so finding the nice recipe and Googling and finding the nice recipe, that's a fetch. Okay, you went and fetched the nice recipe. Okay, then you thought about it. Okay, that's processing. There's something happening in your mind, in your brain. And so that's decoding. That is, you're looking at the recipe. You said, oh yeah, I will need to get these things. So these things that you need to get, you're going to need to get all these food, different items, you know, your raw food items, so that you can do the cooking. That's part of the decoding. In the decoding on the computer, we had to get some data from the memory. So we already got the instructions. Now we have to get some data from the memory so we can process it. Then once we've done that, then we can execute. The executing is us actually going and cooking the food, or it's the CPU actually going and doing the processing. And then the result of the food, we don't throw it away, do we? The result of the food is we present it in some way. And you can think of the computer as presenting that by writing it back into the memory. And that's the end of chapter 3. What I'm going to do is I'm going to stop for a minute, stop recording, and I'm going to set up for lecture 4. Lecture 4 will start in about 3 or 4, 5 minutes, as long as it takes me to set up. So students in the class, maybe you like to go and take a walk while I set up for lecture 4.